We have here measurements and science. The metric measurement tools. It means they use centimeter and meter. We have the first one is the graduated cylinder for liter. This is used for, of course, liquids. Okay. The metric ruler it's also used in the unit of it is in meter. You can use the ruler for measuring everything. The thermometer uses Celsius, okay, for of course heat, things that are not Kelvin measuring. And you can also turn Celsius to Kelvin by a specific equation. We have a metric balance by using the unit gram for weighing things. A stopwatch is unit is used for is seconds. Of course, a stopwatch is for time. Like maybe an experiment, you need to there's interaction, or maybe you're adding or removing things, and this needs a specific time. So we use a stopwatch for it, and the unit of it is in seconds. And we have scales in Newton. This is for the weight using gravity. Okay. We have something called a metric stairs. We have in here in this table metric tools used, metric unit at bench, and used to measure what. This is like further explanation of the previous pictures. We have here a metric ruler. The unit of it is in meter, used to measure distance. A graduated cylinder, the unit of it is in liter. It's used to measure liquid volumes. Anything liquid, you can use a graduated cylinder. A balance, the unit of it is gram, uses the mass or the weight. It means the same thing. A thermometer, the unit is degrees Celsius. You can say 37 or 38 degrees Celsius when using a thermometer, used for temperature. A stopwatch is their unit is in seconds to measure time. Scale is in Newton to measure weight. Okay. Newton is also measured for force. Watt is for power. Okay. Mostly in like electricity, and electricians use that. So in power. A joule is for work. Hertz is for frequency, and byte is for information. Okay, these are the metric units in bench. Now, how do we turn each of the units into what's above it or below it? We're going to use the measure stairs. You have the bench here at 1. Okay, you have here the decimal going to the left and a decimal going to the right. Let's say I want to turn a kilometer into a hectometer. Okay, we're going to take a decimal or one decimal to the left. Okay, so 1 kilometer is 10.2 or 100 hectometer, and so on with a decameter, a decimeter, a centimeter, and millimeter, and so on. Of course, there's a nanometer and micrometer, which is smaller or less than the millimeter. It's like 10 to the power of -5 or -6. Okay. How do we convert each of these units using the stairs bench? Locate the known metric unit prefix on the metric stairs. Okay, we're going to choose any of these. Let's say we choose kilo. Locate the unknown unit prefix to which you want to convert the unknown metric unit. Okay, like let's say I want to convert a kilometer into a meter. Count the number of times you would put your foot down a new step if you moved onto the steps from the unknown metric unit prefix to the unknown metric unit prefix. Okay? Like if I want to convert a kilometer into a hectometer, how many steps do I need to take down the stairs? Only one. So I'm gonna take 1, 0 of them. Okay. Now we're gonna decide if you want to go left or down the metric stairs. Do I want to go higher, like a mega or something more than a kilo, or do I want to go lower, like a deca, a deci, or a centi? Okay. Now I want to turn a kilometer, and I want to turn it into convert it to something less. So I'm gonna take a step to the right. Okay. Move the decimal, this one, the number of the steps you took, in the direction you went, in the known number, and now we have converted the unknown metric unit number. Okay? Like let's say 250 milligram. How do I convert it to 100 to a data? Okay? First, we have the known, which is the milli. The unknown is this. Okay? We're going to count how many steps do we need to take in order to convert a milli into a deci. We're going to take we're going to take 2 steps in the direction to the left. So, according to this, we're going to move the dot 2 units. Turning a kilometer and turning joules, turning decimals, and so on. So first you have to know, or you have to decide what is the known prefix unit. You are going to look at the stairs. Do you want to move right to increase the value, or sorry, left to increase the value, or right to reduce the value? You're gonna count how many steps you need to take. Like if you want to convert a kilo to deca, you're gonna take 2 steps. If you want to turn it a kilo to hecto, you're gonna take 1 step, and so on. According to this number of steps you take, you're gonna move the dot or the decimal in the number with the direction that you chose. Okay? We're going to study some like examples of how to measure specific things. We're going to talk about the erythrocyte or the RBC. The geometry of RBC or erythrocyte is a biconcave disc. It means it's not full circular in shape. Okay, it just doesn't just look like that. It has a concave surface like this one. This geometry is illustrated in this figure. There is a difficult geometry for exactly calculation of the surface area of the volume because it's not like a full circle and you just measure the radius of it and that's it. No, because it's not a full circle. It has a concave curve like this. The RBC maximizes its internal volume to carry a hemoglobin, the iron containing protein pigment, and contains 90% of the dry mass of the cell. That's why this is the reason of the RBC it has concave in shape. The mature mammalian RBC has no nucleus. The RBC of the other vertebrates, such as reptiles and birds, do. Okay? And they have no mitochondria and no endoplasmic reticulum. And their only cytoskeleton is which supports the plasmella, such as a filamentous protein spectrum. These modifications increase the volume availability to carry hemoglobin. So basically, this says that the RBC has a concave in shape and it doesn't have any internal mechanisms like mitochondria or endoplasmic reticulum because this helps the RBC to carry out the maximum amount of blood or the amount of sorry of the hemoglobin to carry it throughout the human body. This is like the main reason why the RBC is in concave. The volume of a spheroid with concave caps is given by this formula. They are not the same formula as the uh, a normal circular radius where we just divide pi over 4. No. The volume of the concave surface with caps, the concave caps, we equals pi over 4 by t, okay, which is this thickness. This value is multiplied by d squared, which is the diameter, minus d by t over 16 plus t squared over 6. We're going to take out the result or the value of this equation, and we're going to take out the value of this equation, and then we multiply the two sides to take out the volume result. Now we're going to know what each of these symbols mean. T is the maximum thickness of the RBC. Okay, so in the equation it gives you the maximum thickness, you're going to compensate by putting it instead of the T's. And D is the diameter. For this formula to work, D, it means the diameter, and T, the thickness, must be in micrometers. Okay, so if the equation was in meter, centimeter, kilometer, we have to convert them into micrometer by using this stair method that we just learned previously. And the volume in micrometers squared. Okay, so if they give you the volume and other than that, also you have to convert it. Calculate the volume of an erythrocyte in micrometers squared. For a typical value of a human erythrocyte, the thickness is 2 micrometer and the diameter is 7 micrometer. It's important for the erythrocyte to have a large surface area for gas exchange. So this also contributes to the function of the RBC. So it's not only concave to carry large amounts of hemoglobin to distribute throughout the human body, it's also large in the surface area. And this is very important for gas exchange during the movement in its circulatory system. The surface area of the spheroid with concave caps. Here we calculated the volume of the entire blood content of the RBC. The second equation is how do we measure the entire surface area of a spheroid with concave capes. The area is or equals pi by the diameter, open between brackets, diameter divided by 2 plus 2 multiplied by thickness, okay, sine to the power of minus 1, okay, by the s. S is shape factor. How do we know what the value of this x is? By using a further equation, is by the equation of the shape factor is 2 multiplied by the square root of 9 by the diameter squared minus 4 by the thickness squared. All of this result of this equation is further divided by 5 multiplied by the thickness. The inverse hyperbolic sine, which is this, all of this symbol, refers to the inverse hyperbolic sine. Function can be represented by ln, open brackets, x plus the square root of x squared plus 1, where ln is the natural logarithm function. Okay? Now, we're going to talk about biomechanics. In this unit of biomechanics, we're going to discuss Newton's law of motion, vectors and scalars, force, speed, velocity, and acceleration, torque, muscle in joints, and pressure. For example, flow of water up a tree. First, we're going to take the law of motion, or Newton's law of motion. Now, according to each scientist, each of them said their version of the law of motion. According to Aristotle, the natural state of motion is rest. Okay, so Aristotle thought that the moving objects or the natural state of objects in motion is rest. Where there is motion, it must be caused by external agent or force that overcomes the natural reluctance of object to move. Okay, so according to Aristotle, it has to have the object is in a state motion, and it must have an external agent or an external force for it to move. This is of course incorrect, the law of Aristotle. After him came Isaac Newton, which of course has or puts the law of motion, which says the natural state of motion is uniform progress along a straight line. Motion is constant and at constant velocity and zero acceleration in the absence of force. Okay? Acceleration is caused by external forces. We all know the Newton law of motion, of course, is the correct one, because he said that the natural or the normal state of motion is in a straight line, and the motion is in constant form where the velocity of zero unless it's affected by an external agent or an external, external force, which will result in acceleration. Newton's laws of motion. An object either moves in a straight line at constant velocity or remains at rest if no external force acts upon it. Okay? So, number one is the general law of Newton. Number two, force equals the mass multiplied by the acceleration. This force that will affect the motion of any object, we're going to know its value by multiplying the mass by acceleration. Force equals mass by acceleration. Force and acceleration are vector quantities, okay? And mass is a scalar quantity. That's the difference between them. For every force, there is an equal and an opposite reaction. Okay. Motion in one dimension. We have here the x-axis, and the force equals the mass multiplied by acceleration. Ergo, the acceleration equals the force divided by mass, by of course doing a cross multiplication. So if we have the mass of this apple is 50 gram, and the acceleration is 9.881 meter per second squared, is an acceleration due to gravity. Okay, so the question brings like the equation, of course, there is the gravity or the acceleration of gravity, and they don't give you the general uh, value of the gravity. It's 9.81 meter per over second squared. What is F? Okay, so we're gonna say F is m, which is 50, multiplied by 9.81. Okay, and we're going to know the value of the force. Force is a vector quantity. Vectors have both magnitude, it means length, and direction. Okay, we have here the y-axis and the x-axis, of course, and vectors will have both length and direction. Magnitude or length of a vector. We're going to use the Pythagoras theorem. How about we take a break and we'll continue after, okay?